But I am going to talk about not so fancy things. I'm going to talk about reactive transport. And I will follow the approach contrary to my distinguished colleague who spoke before. Olaf, I don't see you. Hi. And try to convince you that, yes, you need to do reactive transport. This is basically the main goal. And then present the methodology and all these equations that I think that 5 people at least have already presented. I will derive them for you to know that they don't come from the sky. But before that, just to frame the problem, and because, yeah, of course, the most difficult problem, not in porous media, in the world, is the one I am dealing with. So what are we talking about? So the first 2 days we talked about fluid flow, single phase, multi-phase, and basically remember that came from equilibrium of forces, momentum conservation and mass conservation, and then we get this very simple equation that Fourier started working on at the beginning of the 19th century, so it's a well-known equation. He himself derived many analytical solutions, but which requires specifying a lot of parameters. And some of these parameters vary dramatically over many orders of magnitude, so that the solution will depend very much on the variability of hydraulic conductivity. But the equation itself is simple. And then yesterday, we devoted a lot of time to solute transport, and Marco in the morning derived this equation, or a similar equation. Well, a similar equation, and this is the difference between physicists and hydrologists. Porosity. I like you, Olaf, when you started writing porosity, but then you divided by porosity. I felt so badly betrayed. You never divide by porosity because we are in a porous medium, which is a continuum. We treat the porous medium as a continuum. Everything we do is per unit volume of porous medium. If you divide by porosity, basically you are multiplying by the volume of porous medium and dividing by the volume of water. So you do everything by unit of per unit volume of water, this is what physicists do. Because I am not writing here, this is in omega. What they never tell you is that omega, when you put here velocity and you get rid of porosity, is the void space, which is geometrically awful. So please, don't divide by porosity. So we have here our honest Darcy's law to compute flux. We have porosity. These are easy, very honest parameters. The one that it is not so honest is dispersion. But remember the second day, I believe it was the second day, when Green said, well, dispersion is hopeless. So you just take 1/10 of the domain and that will do it. That will not quite work for reactions, so I will qualify that later. But yeah, it is an easy equation. When we go to reactions, reactions, oh, by the way, so we need to specify only dispersivity and porosity. So going from here to here is extremely simple. Not so many parameters. When you go to reactions, actually it's even simpler because basically I put these dispersive and advective terms as a linear operator. And the only difficulty here is that we have many species. And so it is going to be complex. Reactive transport is going to be complex in the sense that you have many things. You have many species moving around, and you microbes, electron acceptors, electron donors, whatever. But from a conceptual point of view, it is trivial. All you need to add is, the conceptual step, from here to here, a sink source term. And say, oh, but this sink source term is all reactions. Yeah, okay. So we have chemical reactions. It is called reactive transport because to transport you add chemical reactions. So you add a sink source term with the chemical reactions. But in terms of additional data, 0. You do not need, so I disagree strongly that you need to add all these parameters. No, you need to have a geochemist next to you, or perhaps a biochemist, who tell you, okay, the equilibrium constant for gypsum is whatever, 10 to the minus 6.4. That's it. You need to have the geochemist, huh? And so the real challenge is to learn to speak with the geochemist. And if you do microbes, this is an even stronger, more difficult challenge to learn how to speak to the microbiologist. But from a conceptual point of view, just as exhaustion. And if we go further, next week you will be talking about mechanical deformations and induced seismicity and all these things. It's even simpler, because the equation, we go back to a simple elliptical equation. It's so trivial. So, but of course, but then you need initial stresses, you need all, and then up to here, all our state variables were scalars. The concentration is a number at every point. The concentration of sodium is 17.3. Here, your state variables are tensors, which, so it is, in that sense, it is complex. But the point I want to emphasize is that while the mathematical complexity appears to increase when I move down here, the practical complexity decreases dramatically. In all these things, the real, and I am talking now out of experience, the real difficulty is here. So all these discussions that we had the first few days, and I hope you will discuss the next some days, and all the geophysics and all that comes into place, because this is the guy that kills us. This is the guy that makes our life difficult. The boundary conditions, the recharge, we never know the recharge. Well, in Germany, yes, because in Germany it rains so much, you have no evaporation, recharge is easy. But you come to Spain, where the potential evaporation is 3 times the actual rainfall, it's hopeless. This number is very difficult. So this is difficult. This is much easier. This is the easiest of them. So don't think reactive transport is not difficult. And I'm going to try to convince you that even the maths, the practice is trivial, but even the maths are not difficult. The other side of this is that we have conceptual difficulties in all these fields. We do not know mixing. We do not know how to interact this mixing with the growth of bugs, etc. We don't quite know how to anticipate induced seismicity. So, and the reason why we don't is because this field, porous media, is science now. They are trying to convince in the Interpor people that we have a field of porous medium. And it is an awful field in itself. Porous media are not like liquids or solids or anything. It's just pure surfaces interacting with the rest of the world. And as a science, it is just starting, which is a challenge, but it is also a great opportunity. So you've chosen a right field. This is a very exciting field to work in. I am going to concentrate today in this particular one, on reactive transport. And reactive transport, yeah, basically is, as I said, transport, advection, dispersion, mixing, all that stuff that we were talking about yesterday. Reactions for a physically oriented person like me look awful, because chemists always come up with new reactions, and they are like cooks. You say, tell me the recipe. Well, you put a little bit of that, but how much? So I tried. So in practice, yeah, you need to work with someone who knows. But really, once you choose the reactions, or the guy who knows chooses the reactions, everything else is easy. And really the real problem here is that you need to choose a good semantics. If I did not have the word table and I had to describe what this is, well, this is a flat surface where you can put your computer or write or whatever. It has some legs, 3 or 4, I say there. This one has only got 2, and it is still a table. So if every time I have to describe that, I had to go through that description, it would be impossible. But as soon as I say table, it's so easy. Not only it's easy, but once I have the word table, I can think of chairs, I can think of furniture. So choosing the right semantics allows me to grow. In chemistry, this is essential. And it will not come out from chemists, because they were not trained into that. So are there chemists here? Microbiologists? Sorry. Monica, no? Sorry. But please, listen to this. So, yeah, there are many reactions, so we need a... Now, the first ingredient is chemistry. Solute transport. We already know, so it's basically the mass conservation per unit volume of aquifer. Storage term, dispersion, advection, and reactions. So these are the reactions. This is the term we are going to deal with, and I will often lump all this together just for compacity into the transport operator, which is linear. And no matter how fancy this mixing thing, blah, 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 comes up, the transport equation will always be linear. So the transport in itself is a linear phenomenon. So, chemistry. The problem with chemistry is that, yes, as soon as you start, you have 1, 2, 3, 4 species here. And this is a very simple problem. It's just the carbonate by carbonate type of carbonic exchange. For each of them, I have a mass action law, and I have activities. And when you get into real problems, very soon you have 50, 20, 100. I was once in a thesis where the lady had, to describe her system, had 3 pages of equations. 3 pages of just chemical reactions. And then when it came to write the mass action law, it was another 3 pages of mass actions law, which were all basically things like that. The product of the activities of the products divided by the activity of the reactant equal to a constant. During the defense, I said, well, in the second line, in the second page, line 17, there is a mistake, and she went like that. And I assume the PhD advisor works, because, I mean, it's impossible to read that. Now, if you say, okay, no, what I'm going to do is, all these reactions are basically species with some coefficients here, so it is so easy to write as a matrix product. So I describe my reactions by a stoichiometric matrix, where the coefficients in this matrix are the coefficients in this reaction. So I don't know. The first row. So I have 1 column for each species, 1 row for each reaction. So it's proton 1, carbonate 1, bicarbonate -1 because I took it to the right hand side. And in this reaction, what is the third one? The fourth? Oh, HC, carbonic, sorry?
The convention is opposite. It's negative for the left and positive for the right.
No, it's the opposite. It's, I put everything on the right hand side. Think that I put everything in the right hand side, so this comes to here with a minus. But here, sorry, and here I am not specifying what are the columns, so it's not a very good example. But anyway, the point is that if I take the logs here, what I end up is with these coefficients, because the activities are, the stoichiometric matrix coefficients are exponents in the mass action law. So if I take the logs, they come out in front. And all these equations, whether I have 3 pages or I have 2 like here, I can write in this way. And this is very convenient, because from now on, whether I am talking with 100 species and 50 reactions, or with 2 reactions and 2 species and 1 reaction, I will always write it like this. So this is my table. It's not something with many 2, 3, 4 page flat surface, whatever. I am going to write reactions, the mass action law of chemical reactions, just like this. So, so this is the nomenclature I'm going to follow. I will, if you are inclined to algebraic structures, etc., everything that you learned about vector spaces fits here, and it is extremely convenient. Two of my best papers have written simply by applying concepts that I learned when I was in my first year algebra, and applying them to reactive transport. So the ingredient 2 is chemical reactions. And again, I take the chemical system similar to the one before, plus I have a calcite dissolution. And then the stoichiometric matrix in here, I am putting the columns right. So I have 1 row for each reaction, reaction 1, 2, 3, row 1, 2, 3. and one column for each species. So I don't know, for instance, bicarbonate has a 1 in this reaction, bicarbonate a 1 in this reaction, and a -1 in this reaction. So these are the coefficients. The coefficients in the reactions are the coefficients in my stoichiometric matrix. Now, the nice thing about that is that if I now define Ri as the mass I am going to measure in moles out of convenience. So if Ri, the reaction rate, is the number of moles of reactants that go into products per unit time and per unit volume of aquifer, my reaction rate, the overall reaction rate, being the contribution to the mass balance of each species from all these reactions, is just this stoichiometric matrix multiplied by the reaction rates by the small r's of these reactions. And that is, now it's getting involved. Well, not really. I think a little bit more carefully. So we have the mass balance of protons, for instance. The mass balance of protons would be the transport of protons plus the terms coming from the reaction rates. And the terms coming from the reaction rates are, if I have R1 moles coming this way, it means that I am taking R1 moles of protons out of the system. So it would be minus R1 here. And the same with the other two reactions. So basically, the contributions to the mass balance of each of course, now when I start writing even for this very simple system, I have 5 transport equations, which looks heavy. But really, if I write it in matrix vector form, and I recall that these coefficients here are really the coefficients here, all my transport equation becomes just like this. So, oh shit, I forgot the porosity. I apologize for that. So the transport, I put an M here because some species are not mobile. Calcite does not move, therefore for calcite this matrix would have a 0 in the diagonal. But this is it. So this is from now on, this is going to be my reactive transport equation, which I write in matrix form, and which, it can serve, as I said, for 2 species, 1 reaction, or 100 species. 50. I am distinguishing here between fast reactions that occur in equilibrium, and slow reactions. In essence, homogeneous reactions that occur in the aqueous phase, they have characteristic times of micro or nano to microseconds. So, those are really fast. We are interested in things, Olaf is interested in things of days. I am a groundwater hydrologist, I am interested in things of years. But compared to nanoseconds, I can assume that this reaction is instantaneous. So aqueous reactions, we are typically going to assume instantaneous. Heterogeneous reactions that occur with the solid phase, well, it depends. Sometimes it will be fast, and it depends on your problem. If you're solving a problem that occurs like Maria, she's not here, Maria yesterday, it was 6,000 years. The typical equilibration time for calcite may be a few days, so she assumes calcite dissolution to be very fast. But if you are interested in some other things, calcite dissolution, you may want to know the kinetics of that. So there is modeling. Modeling, the thing I agreed most with Olaf is that in each case you have to find out what is relevant and what is the controlling factors. So sometimes a given reaction you may wish to treat as kinetic or as equilibrium. But anyhow, even if I write it like this, notice that here I have NS transport equations, NS being the number of species, and if I have NR reactions, I have NS species concentrations unknowns plus NR, the reaction rates unknowns. So if I have 100 species and 50 reactions, I would have 150 unknowns per point in space and time, and that is shit. it's not conceptually difficult, this is it. So it's still my transport equation with some sink source terms. But it is heavy, and it is computationally involved. So basically, what we want is to do, I'll show you a few tricks to do this very fast. And it can be done very fast, indeed. But then the first question would be, well, is it really needed? And sorry, I wrote this before knowing your presentation. I mean, there are people who will say, no, why do you go through all this pain? All you need to know is the residence time distribution. And if you know that, I don't know, if you want to simulate radioactive decay, and you have a solute with a half-life of 12 years, and your residence time is about 12 years, you know that the concentration at the outside will be half of the concentration in the input. That's it. So, and of course, Olaf made it a bit more sophisticated, but in essence, what he was saying is, no, you don't need to go to do, all you need to know is the residence time distribution, or to be a bit more sophisticated, how was it, the cumulative exposure time, how much time a given water parcel has been exposed to reacting surfaces. And then you don't need to go through all this mixing and dispersion and all that. But of course, my point is that it is needed. And to argue that it is needed, yeah, the answer is yes, it is needed. It can be understood and it can be solved efficiently. Another question is whether we know how to do it. But this is, I am hoping for you guys, Marco, Tanguy, Emmanuel, to tell us how to do it. But just to argue that it is needed, I will continue with an example that, I will start an example that Maria finished yesterday. And this is what happens in coastal aquifers, carbonate coastal aquifer, any Mediterranean coastal aquifer would make this, where I have fresh water in limestone, salt water in limestone. Limestone is relatively fast, therefore these two are likely to be in equilibrium with limestone, and then they mix. And what happens is, this figure looks very similar to the one that Maria presented yesterday, but no, what I'm plotting here as the independent, you were saying you need an extra additional thing. Here is salinity. So what is changing from here to here is the salinity. I have high salinity here, low salinity here. What happens is that the solubility increases dramatically with salinity, and in fact, at the zero ion strength, at the zero concentration end, this slope is infinity. This slope is infinity, and then it goes like this. And therefore, if I mix, because of this convexity, if I mix, the mixture is going to be undersaturated with respect to calcite, and here I have dissolution, and this is what drives this karst formation in coastal zones and etc. So I don't want to go into the details of how that evolves. This is what Maria explained, but I want to show you a much simpler example. Let's say a diffusion. You have diffusion between salt water on one end and fresh water in the other end, and what happens in between? And well, obviously it is clear, right, that diffusion is going to be 1D, almost homogeneous, linearly varying concentration of salinity and everything. So here in the middle, my water will tend to be undersaturated with respect to calcite. And in fact, what a good geochemist would do is to say, okay, no, I compute the saturation index, which is the log of the, here I should put activities, and in this particular example, this is the key issue, the activity. The activity product, carbonate times calcium, divided by the equilibrium, the solubility product, or the equilibrium constant. This is another thing I hate of chemists, sorry, Monica. That for the equilibrium constant, they have different names depending on the reaction. And then until you learn a lot about reactions, you say, well, why do they call it solubility product? Well, they call it solubility product because for dissolution precipitation reaction, the equilibrium constant they call solubility product. But anyhow, if this is very big, if I have lots of carbonate and calcium, this activity product will be larger than the solubility product, the logarithm will be positive, and then I have precipitation. If it is negative, I have a dissolution, and when it is close to zero, it means that I am in equilibrium. And this is the way geochemists, you give them a water sample, they do a chemical analysis, they put it into freak C, and they give you back immediately the saturation indexes with respect to all minerals, which is very bad, because that implies forgetting that water moves. And this is no joke. Monica, sorry, but don't come out from here realizing that water flows and the solutes diffuse and everything. Most of your colleagues, I mean, they know that water flows, but it is not part of their mental understanding. Because no. So you compute the saturation index and you come up with something like this. And if you do calculations and you can compute how much calcite you need to dissolve to go back to equilibrium, and they get so happy. And in this case, you see, well, the minimum saturation index, or if you want the maximum under saturation, is here at about 20% mixing ratio. So this is fresh water, this is salt water. We are in that diffusion example, remember? So in my diffusion cell, over here I have 20% seawater, 80% fresh water. And if I compute how much calcite I have to dissolve to go to equilibrium, actually the maximum is here. And then the geochemists will start fighting what is the best approach. When you do the reactive transport calculation, everything is dissolved in the fresh water. So if you put a calcite sample between fresh water and salt water, it doesn't dissolve or precipitate in the middle. It dissolves starting from the fresh water end. And then you can go through analysis that say, okay, I do the speciation, I compute the concentrations of all the species, and I get these things, and say, why does it dissolve in the fresh water end? And say, well, yes, of course, because here is where the acidity is coming into place, and if the acidity is moving here, it dissolves, but of course, as soon as it has dissolved, it's got in equilibrium, so there is not so much dissolution capacity left, and very complex, impossible to understand. You do this, straightforward. It may be worth going into this to understand the details of why it is, but believe me, the detail is here. It's on the fact that I have an infinite slope or very high slope here. It is this, and the change in the slope there, which is related to the activity coefficient and blah, blah, blah. So, yeah, another thing. Say, oh, and Maria also talked about this yesterday. What if I reduce the CO2 concentration on the freshwater side? Huh? What is the difference between working in Cancun, where I have a very high activity, so therefore very high CO2 concentration, or in Venezuela, or in, I don't know, in Algeria, where they have very little activity coefficient, very little vegetal activity, and therefore probably much lower CO2 concentration. And you do the calculations of the sensitivity index, and then you say, well, this is weird, huh? When I reduce the concentration of CO2 on the freshwater side, my undersaturation increases. Therefore, I will dissolve more. And then you do the calculation. No, you don't dissolve more. You dissolve a lot less, which makes sense because you have less acidity. Huh? But if you just go blindly with the saturation index, you would be mistaken. So this is the point that I say the interplay between reactions and transport is non-trivial. Saturation index calculations are very interesting and you need to make them, but they don't tell you where, how, when, how much, under which conditions. If you want to know all these things, you need to do the reactive transport calculations. So yes, it is needed. Second, to understand the fate of reacting solids. Isn't it too difficult? And I claim no, it is not really difficult. And the basic tricks is to work with these components. Remember that we had this, this is our transport problem now. So these kinetic reactions from an mathematical point of view, they are a function of concentrations. So from a mathematical point of view, they are easy. They can be highly nonlinear. They can, I mean, everything that is happening in our body is are kinetic reactions. We are alive because we are a kinetic reacting system. If we were in equilibrium with the environment, we could be all CO2 and water, and that it would be not very interesting. So I don't want to trivialize this. Kinetic reactions are important, and every time you get excited about something, it's because there are some hormone production. These are biochemical reactions going on in there. So the whole life is in here, but mathematically trivial. So the ones that are tricky are these ones, because these ones do not depend on concentration. I don't have an equation for them. So what do? I get rid of them. And I get rid of them by using, I multiply by the kernel matrix, by a matrix that is perpendicular to this, orthogonal to this stoichiometric matrix, and I get rid of them. So instead of working, now I multiply all this by this components matrix, and you could say, is it possible to find it? Yes, always. Not only do you have a vector space of dimension ns minus nr to choose the components matrix, and then I fight with people like Olaf on which is the best way to choose the components matrix. So this matrix always exists. There are many of them. It's easy to find, and I simplify further my equation because I get rid of this. And what is more important, instead of working with the concentration of a species, I'm going to work with the concentrations of components, which are ns minus nr. So I go from this problem in which I had ns plus nr, 100 plus 50, 150 unknowns, to a problem in which I have 100 and minus 50, 50 unknowns. So from 150 to 50 unknowns. I have simplified quite a bit. Simply by doing that, not only I have simplified, but I have got rid of this ugly thing. And so what I work with is these linear components. In this example, how to compute the components matrix is not so difficult. Basically, the simplest way, not always the most convenient, but the simplest way is to write the stoichiometric matrix in a way that I have a minus identity matrix on the last ns minus nr, 5 minus 3, no, nr. In the last nr columns, three reactions, so in the last 3 columns, I put a minus identity matrix, and then the component matrix looks like this. And if you do the check, if you multiply this by this transpose, basically you end up with S1 transpose minus S1 transpose, which is 0. So it's easy. And very often, what comes out, this is the component matrix, so my unknowns now are not going to be the concentrations by the components, so I multiply this by the vector of concentrations, and so the first component would be protons plus minus CO3 plus CO2 plus calcium, which I will not try to convince you, but believe me, this is acidity. Acidity, say, well, will you measure acidity with pH? Bullshit. Sorry. It's not an appropriate measure of acidity, not the pH. The reaction, there are many species in water that contribute acidity. If you have CO2, CO2 contributes acidity. So therefore, if I want to know the total acidity relative to bicarbonate in this case, I have to add the CO2, but I have to subtract the carbonate ion. And the second one is HCO3 plus CO3 plus CO2, which is the total inorganic, minus calcite, minus calcium, because I am subtracting, I am also taking into account the carbon that is part as calcite, and therefore this is the total inorganic carbon, which is, it's a well-known type of magnitude. People analyze these things, so I am given data in these terms, so it's good to work with, but yes? Say again?
What runs if you run out?
That's a good question. If I run out of this, then I don't have it. I don't have this reaction. And if I don't have this reaction, it means that my stoichiometric matrix would be like this. And therefore, here, instead of having 2 components, I would have 3 components.
But then you have to switch, so if this happens within your simulation.
I'm not talking about simulations. But what this is telling me is that something that we know happens in nature, and that is that the mineral zonation controls your chemistry. And in fact, if you go back to the very first papers on this by Jacob Rubin, he said, no, reactive transport, you divide your domain depending on the minerals present. Yes, so you have to have from a numerical point of view, you have to have a good way to switch from one to another. In Crunch, you also have this mineral zones and the change in the mineral zone. In fact, I copied this from Carl, this concept of, although it's not his concept, the real origin of this concept is Jacob Rubin. Yes, yes. So, yeah. You have to acknowledge that you have different minerals in different portions of the system, and perhaps in another portion you have gypsum, and gypsum apports calcium, so in another, and maybe there will be areas where you will have gypsum and carbonate. So each of these will be a different mineral zone, and the chemical behavior and everything, but not just the chemistry and everything, they are totally different systems, and you have to treat them as totally different systems. They are different vector subspaces of our. Again, the problem is if you write all this separate like this is a mess, but if you write in components, all you have to solve are the components equations. And this is, it looks complex, but let me make one example. But basically the procedure is like this. You define the chemical system. For this, you need a geochemist. So you work with a geochemist and you define the chemical system and say, yes, I am going to have calcite. If I have calcite, I have to look at carbonate, bicarbonate, pH, water, whatever, calcium. And you define the components. And the components, remember, right? You write the stoichiometric matrix, and the component matrix comes out immediately. Now, if you have the components, it turns out that the transport of components, assuming that you don't have kinetic reactions, is easy. It's just a conventional transport equation. No problem at all. So you solve for components, and now that you know components, that you have the total concentrations plus the mass action loss, you can compute the concentrations of all species. This is what codes like FreakC that you all know, and I never use, but this is what these codes do. Given the components and the equilibrium reactions, they compute the concentrations of all species. And then, now that you know the concentrations of all species, you substitute them back into the original transport equations to compute the reaction range. So this is the procedure, and let me illustrate it for a couple of cases. I'm not sure how am I doing time-wise. Okay, so yeah, can you turn on the light? So let me consider 2 cases. One is the simplest case, in which I have a sorption reaction, in which I have, I don't know, X plus some ion, that it is in equilibrium with this ion plus absorption site. And the equilibrium for this is typically written in terms of, this is solid phase, this is liquid phase. So I'm comparing 2 different things. So here, typically, they measure it in terms of sorbed or solid concentration, which is the mass or the moles of solute, of A, per unit mass of solid. This is the way it's usually reported. And if I plot it versus the concentration for low concentrations, which is when this is applicable, typically this is linear, and they call this equilibrium constant, they call distribution coefficient, yet another name, distribution coefficient when you talk about adsorption reactions. That is that S is equal to KdC. Now, if I write the mass balance, I apply these equations, I have that the derivative of the concentration with respect to time is equal to L of Ca plus the reaction, the amount of moles of this that go into this would be the concentration of Ca. But I also have another equation which would be the derivative of Sa with respect to time. Oh, shit, I have a problem here. This is per unit volume of aquifer. So these are the moles that go from here to here per unit volume of aquifer per unit time. S is per unit mass of solid. Oops. So what I have to multiply by the bulk. Say again?
The other one you have beloved, you have forgotten the beloved porosity.
Oh, thank you. Too many days in this class, in this course. Equal to now minus r, because it's minus r here. So I have to get rid of this, and I can do it in two ways. The immediate one is, well, you just add them up. If you add them up, r's go away. But I don't want to do it the simple way. I want to do it the difficult way because I want to show you how a stoichiometric matrix works. So the stoichiometric matrix, in this case, I only have one reaction. Would be for A, I have a 1 here, and for S, so this would be A, and this would be XA, 1 minus 1. My components matrix, in this case, is, remember, I had it here before, It's 1, 1, yes, but let me, where was it? Here, So this portion is 1. This is the minus identity matrix. The identity matrix, when you only have one row and one column, is a 1, so minus 1. And the components matrix is the identity here, and this one transpose here, so it would be 1, 1. That's it. So what I do now is I multiply this by this. Multiplying this by this is simply this times 1 plus this times 1, which is the same as adding them up. The r's go away. And I end up with the equation which is 5. Actually, Olaf wrote it before. With the same notation. For once, we agreed on something. Equal to LCA. Notice that the r's went away. Now, I use this equation that I just deleted, that I had here, S is equal to KDC. So I substitute S by KDC, so basically this would allow me to write dAdt plus rho B KD. KD is constant, comes out of the derivative, dC dAdt equal to L of Ca. It's still too complicated, so what I do next, I factor this out. I factor the dCA dt out, which would lead to right here. And I also factor out the porosity. So I write phi times 1 plus rho kd divided by phi dC dt equal L of Ca. So this is it. It's simple. It's the same as before. The only thing that I have here is this retardation coefficient. This is called retardation coefficient. And so the equation, the solution for this system actually is basically the same I had before without this reaction term, but with a retardation here. And retardation is very simple because I can put it dividing here. So actually this is the same if I put phi dc dt prime, let me put here dt prime equal L of Ca, where t prime is the real time divided by r. So this is why it is called retardation. People like me who are smokers, you know, in the bus I suffer because I cannot smoke. So every time I say stop, I go down into the stop to smoke a cigarette, and buses keep passing by, which means that all I do, the advection by the bus and the mixing with the people in the bus, is reduced by the rate of the proportion of time I am in the bus stop smoking my cigarette, stuck there against the surface, sorbed onto the surface, But this is it. This is all that happens. The effective time is reduced by this retardation factor. Everything else happens exactly the same. So this was one example. Let me go to another example, which may be more interesting for the purpose of this course. And the other example is that, two species that react to form a third species. So I now have A plus B. Let me do it the other way around. A solid, a mineral that reacts to form A plus B. And then I would have the transport equation of the two of them. I put Ci. I can go as many as I want. L of Ci plus R. In this case, one more here. A and B increase in 1. So in this case, my stoichiometric matrix would be 1, 1. You could say, oh, you need a -1 here. Yes, but for now, let me ignore this. For now, I am not going to worry about what happens to the solid phase. If I had more time, I would. But for now, let me forget. I'm not going to worry about the concentration of the solid phase at this stage. Now, the U, using this same equation, would be 1 minus that. Oops, shit, this doesn't work. Whatever. 1 minus 1 still works. Which points that in this case, if I have here the concentration of A, and I write the same thing with the concentration of B plus R, what I have to do is to subtract to get rid of this. And this is the meaning of this stoichiometric matrix here, of this components matrix. So my component now will be Ca minus Cb. And the transport equation that I have to solve is phi by subtracting concentration of I minus concentration of B is U, du dt, equal L of U. So this is easy. So I solve for U. But I know they are in equilibrium. So this is step 1, find the chemical system and the components. Step 2, solve for the components. Step 3, speciation. For speciation, I know that U is equal Ca minus Cb, but I know that they are in equilibrium, so the equilibrium constant is Ca times Cb. And then I can, this is a very simple system to solve. I would solve it if she was not looking at me with that face, but since she's looking at me with this, this is the solution. You just solve for C1 here, is C1 is equal to U plus C2, and plug it here, you end up with a second degree equation, you solve it. This is the solution, C1 and C2. Now the most interesting thing, I need 2 minutes, how much do I have? 1, shit. Because so the point is that I can compute Ca and Cb as a function of U. So the most interesting thing comes now, because then say, oh, but let me go back to the first equation and see that here everything is a function. Ca is only a function of U. If Ca is only a function of U, it means that when I write the derivative of Ca with respect to t, what I have, this is really the total derivative of C with respect to U. C only depends on U, times the partial derivative of U with respect to time. And if it is a gradient, same thing, gradient of Ca is dCdA with respect to U times gradient of U. And if I have here another one, shit, this is more difficult. If I have if I want to do a second derivative of this, the gradient of d grad C, is more tricky because now it's the derivative of a product. So I have to first take the derivative of this, second derivative of Ca with respect to U twice, times I have to multiply by this, so it would be grad of U transpose d grad U, plus, and now is the first term, dCa dt, the second derivative of this, multiplied by d because it was here, del d del C, del U. So now I have all these terms, I plug them in that equation. I plug them in the equation, and what I end up with is this dCA du that I have everywhere here, notice, huh? Oops, this is u. This dCA du I have everywhere, so I factor it out, is dCA du times everything else, huh? du dt plus q, porosity, shit. Olaf. Phi dc du, grad u, excuse me, minus del d grad u equal to whatever is left, and whatever is left is r minus this term. There was a 2 missing somewhere, huh? But you see that I am not very capable of doing these things in the screen. But there is a 2. There is a 2 missing here somewhere. Grad u d grad u transpose here. But this was 0 because I solved the transport equation, so this is 0. And therefore r is equal to this equation that you've been using all the time. But you see, it's not difficult to get. All I did is to realize that in these equations, C is solely a function of components. And you can say, oh, but there is some external function. It is also a function of salinity. Okay, so I add salinity, and then here I may have to derive with respect to more factors. So this eventually may end up being a full Hessian with all the components that affect my concentration. If it is temperature, salinity, whatever, I may have to put there. But the essence is that, yeah, this is it. And this links with what we were doing yesterday, that reactions are basically, fast reactions are basically the result of mixing with some chemical influence plus time for kinetic reactions. And this is where we are now, because everything is easy, or everything would be extremely easy if we knew how to represent mixing properly, but we don't. And this is our, let me just put one transparency to say, because yesterday we were talking at the pore scale, but at the macroscopic scale is the same thing. The macroscopic scale now, these are the type of pictures that Olaf was plotting. Yeah, one thing is the rate at which things spread, and another thing is the rate at which this mix. Everything is happening in here. And what is happening in here occurs here at a very small scale, is at the pore scale. So all the work that Tanguy and Marco and Emmanuel were presenting yesterday about this weird thing, oh, this is a pore, who cares about the pore? Yes, we do care. This is everything, all the reactions, and Olaf now he has sold himself to the kinetic people, and he concerns also only with residence time distribution, but in the old times, he was very much concerned with these things that we call transverse dispersion, and we do not know how the hell to compute it. Remember that when I didn't say that each L had to be the same. So if I have LA and LB, if this was LA and LB, I would still do exactly the same thing, things would get a bit more complicated here, so I wouldn't get such a nice expression, but it doesn't matter. It would still, the reaction rate would still be driven by mixing, except that mixing now would depend on the two of them. What I multiply by this components matrix to get rid of this. What really bothered me are these fast reaction rates. Whether each species is transported with the same dispersion coefficient or not, I don't care. It is not important. So the disagreement with Olaf here comes, they say, well, if sodium is displacing much faster than, say, chloride, it creates an electrical imbalance. So what they know is that these electrical forces are much faster. I mean, you get a driving force that compensates for this imbalance. A different issue is when you work with neutral molecules, and organic compounds sometimes are big, they have a smaller diffusion coefficient, and then you have a, yeah. It may have a slightly different transverse dispersion. Well.
I would say, maybe I'm wrong, because you can correct me, but you develop all these ideas thinking that A is the red and B is the blue, so the dispersion is the same for both. Do you agree?
No, no. It doesn't have to be the same. I mean, in my papers, in all the papers I've written, yes, it is always the same, and there are people who argue they have to be the same for the reason I said, because of the electrical forces, but it doesn't really need to be the same. But I would say again, I get back to you now, from an engineering point of view, we are so far from that. Our real challenge is the mixing rate. But for instance, for gases, we do it for gases. In gases, the diffusion coefficients are dramatically different. And gases are neutral. So, yeah, and there you must acknowledge that the different diffusion coefficients. We do exactly the same thing doing this. It is computationally, it's a bit of a pain in the back, but it's not too bad.
So we have time for one very quick question. Can you apply the same matrix like this is for the unsaturated case?
Oh yeah, yes. Yeah, here, I didn't say here at all where this Q comes from. Actually, this would be volumetric water content. And actually, Kino did it yesterday. Yeah? He was using these same equations for the unsaturated case, in which case this is water content, and here when I put the Q, the computation of the flux, it is trickier. The computation of the dispersion, but this is what Kino was discussing yesterday, the concepts of dispersion are much trickier. The separation between, remember what he was showing there, this path going very fast, he had huge dispersion, yet very little mixing. So the separation between dispersion and mixing is even more dramatic in unsaturated than saturated, but the basic concepts are the same.
And also for the other kind of suction,
Say again?
for other not equilibrium suctions, I don't know what can you
Yeah, well, for non-equilibrium, all these tricks do not work very well for non-equilibrium. For non-equilibrium, you have to do the computations, the full computation. The point is that what makes complicated this is not kinetics, and this it was demonstrated, if you allow me to say, beautifully by Olive. Kinetics is easy to deal with. The trick is the mixing, and sometimes kinetic reactions are driven by mixing as well. So that to put all this together, it may be tricky, but, and this mine was a lecture, was not a research lecture, but if I had chosen to give a research talk, I would have said that nowadays we don't do, I mean, we simplify things a lot. All you need to compute are the mixing rates. If you have the mixing rate, we use kinetic time like Olaf. Basically, it is very easy. So we do not even solve for all concentrations of all the species. This is calculations that are done locally. All we need to compute numerically in our codes right now is the mixing rate. That's it, which is a scalar. So you only have to solve one transport equation, and all the reactions come for free.